Let's see this question. In this question, they're asking something about rank and eigenvalues. So let's just read out this question. Let A be n cross n matrix with characteristics polynomial minus lambda into lambda minus 1 square. So some characteristics polynomial is given. And now from this polynomial, you can definitely infer that correspondingly, corresponding to this polynomial, you can definitely say that lambda equal to 0 and lambda equal to 1 comma 1. I'm writing 1 2 times because this is repeating 2 times. So these are the 3 eigenvalues. Although distinctly there are just 2 eigenvalues, but total there are 3 eigenvalues. And what are those? Lambda equal to 0, comma 1, comma 1. Why I'm writing 2 times? Because it is repeating 2 times. Now let's just see what they're asking is that explain whether or not following can be true, and if it can, give an example. So basically, you just treat this as an MSQ question. So where they are saying that explain whether or not which of the following can be true. So they are asking, can the rank be 0? Can the rank be 1? Can the rank be 2? Or can the rank be 3? So what are the possible values of rank? That's what the question is. One thing is for sure, that if lambda is 0, then rank cannot be full rank, which means that full rank means this the degree of the polynomial is 3. So that's why the matrix A must be 3 by 3 matrix, right? So A must be 3 by 3 matrix, and because that lambda equal to 0 is there. I mean, there are 3 lambdas, that I agree, but one of the lambda is lambda equal to 0, right? Since lambda equal to 0 is there, that's why rank cannot be equal to 3. Reason being is that determinant is 0. I mean, there are multiple reasons. So determinant of A is 0. It means that it cannot be full rank. It cannot be full rank. Cannot be full rank. Full rank means that rank cannot be 3. So rank cannot be 3, which means that this is definitely not the answer. Now, can the answer be A? Can the answer be B? Or can the answer be C? These are this is the question that they are asking. Now let's just understand this bit more carefully. So what they are saying, that one of the eigenvalue is 0. This is what they are saying. So let me just go to the next page. See, how do you find the eigenvector? Is basically like this: a minus lambda I into x equal to 0. I mean, you just solve this kind of equation for corresponding to lambda equal to 0, for lambda equal to 1, like that. This is how you find the eigenvector. I mean, this is a way to find the eigenvector. Do you understand? I mean, once you know the eigenvalue, based on that eigenvalue, you find the eigenvector using this equation, which means that let's suppose this is, I mean, after putting some lambda, maybe lambda equal to 1, lambda equal to 0, whatever lambda you are putting. So this is one matrix that we get, right? Let's just call this matrix A prime. So the equation is basically A prime into x equal to 0, isn't it? Now I'm asking you to solve for the x. Basically, this x is an eigenvector corresponding to lambda. So suppose you are putting lambda equal to 1. Now, if you are putting lambda equal to 1, you get a minus 1 into I, which means a minus I, which is some a prime, right? Now, a prime into x equal to 0. So you are solving for x. So x is eigenvector here. I hope that is clear to everyone. X is eigenvector. Actually, these things are already covered in the course, but still, like if you want to recall, that's why I'm just telling them again. Okay. Now, say here x is one eigenvector. That is clear to everyone. Now let's just understand that how to interpret this idea. So basically, if you solve this a minus lambda I for lambda equal to 0, then this thing is just a only. I mean, if you put lambda equal to 0, if you solve for the eigenvector corresponding to lambda equal to 0, see the eigenvector corresponding to lambda equal to 0, I am solving for the eigenvector corresponding to lambda equal to 0. Then it is as good as saying that you are solving for x equal to 0. See, first of all, you should understand two things. One is that ax equal to 0 is one set of equation. I mean, we call it system of linear equations. And specifically, if you want to call, then you just call it system of homogeneous linear equations, right? Or homogeneous system of linear equation, whatever. So basically, this is one system of linear equation that should be clear to everyone. Now, there are another set of system of linear equation which is something like this: a minus lambda I into x equal to 0, right? So this is some other set of linear equation. This is some other set of linear equations. Now, if I just ask you what is the relation between a and a minus lambda I, then what is your answer? Honestly, there is absolutely no relation at all, which means that whatever is the solution for x equal to 0 could be very, very different for the solution of a minus lambda into x equal to 0. See, if I just tell you, okay, maybe I can go here. Suppose this is 1 2 3. This is I mean, let's suppose 2 4 5, and this is, let's suppose, 3, 6 and 8. Okay, this is one matrix. And if I have one more matrix, maybe something like this. Let me just quickly have one more matrix. So suppose this is one matrix and you have one more matrix which is suppose something like this. Maybe I can just copy this, right? Maybe I'm just differing one of the value. Maybe let's suppose this value is something like this, maybe 10. Okay, something like this. So basically one of the value is differing. Then if just by one of the value these two matrices are actually not same, which means that the set of all linear or the set of solutions here at this matrix and the set of solution here at this matrix might be completely different at all, right? So that is why I'm saying that there is no relation between A and A minus lambda I. So first of all, there is no relation. That should be clear to everyone. But interestingly, both are getting glued to each other or both are getting converted to each other if you put lambda equal to 0 in this equation. Which means that if you put lambda equal to 0 here, okay, you put lambda equal to 0 here, you get Ax equal to 0. Which means, now just try to understand this very carefully, that if you want to solve for the eigenvector, see this x is actually eigenvector, right? Here this x is eigenvector. If you want to solve for the eigenvector here, and here this x is a system of, the solution of x equal to 0, right? So if you want to solve for the eigenvector, and if lambda happens to be 0, then actually it is not only the eigenvector. This is an eigenvector. That is I'm saying, I'm not denying this fact. This is an eigenvector. Definitely it is an eigenvector. But this is also, for lambda equal to 0, this is also the solution of x equal to 0. That's very, very interesting, right? See, this x and this x is same if lambda equal to 0 if you put. So basically the conclusion here is that that if you put lambda equal to 0, then the solution of x equal to 0 and the eigenvector corresponding to lambda equal to 0 are both same. So let me just write it down, that eigenvector corresponding to lambda equal to 0 is same as solution of Ax equal to 0. So this is one key point that you need to understand first. Okay, this is one very crucial key point. Okay, now let's just extend this idea a little more. So suppose if I have just one eigenvector corresponding to lambda equal to 0, then how many solutions you have for x equal to 0? Just one, right? So you can say, suppose you have just one eigenvector. Okay, so number of eigenvectors, I'm writing number of eigenvectors corresponding to lambda equal to 0. So this is number of eigenvectors corresponding to lambda equal to 0. Suppose you have just one eigenvector, then this is basically, here I'm writing number of solutions of x equal to 0. Then how many solutions I have? Exactly, this is one-to-one mapping, right? If you have one eigenvector corresponding to lambda equal to 0, then you have one solution. You have two eigenvectors, you have two solutions. You have three eigenvectors, you have three solutions. You have four eigenvectors, you have four solutions. So this is exactly one-to-one mapping, because these two are exactly same things, right? So that's why if you have two here, you have two here, you have three here, you also have three here, you have four here, you have also four here. There is no difference at all. So why do discriminate between these two? I hope you got my point. So basically, whenever I say number of eigenvectors corresponding to lambda equal to 0, whenever I'm saying number, it always means linearly independent solutions. Okay, number of linearly independent eigenvectors, basically number of linearly independent eigenvectors, number of linearly independent solutions. Okay, otherwise there are obviously infinitely many eigenvectors corresponding to any lambda, because if x is eigenvector, then kx is also eigenvector. That's what we already know, we have already seen in our course. So here, if I say the number of, okay, I'm just omitting this term for the sake of our I can say our convenience. Okay, for our convenience, just I'm omitting this term. Otherwise, you just keep this term as implicit. Otherwise, the whole discussion will not make any sense, because by default there are infinitely many eigenvectors. By default there are infinitely many solutions. If at all there is one solution of x equal to 0. If x is one solution, then kx is also solution, because you can just multiply by the k both sides, right? K into 0. Anyway, let's not worry about it. So if I'm saying the number of eigenvectors corresponding to lambda equal to 0 are 5, then number of solutions corresponding to number of solutions of x equal to 0 are also 5. So basically here this number of solutions or number of linearly independent solutions are also called a nullity, right? That's how the nullity is defined, and that's what we have understood in our course. So I can say that number of linearly independent eigenvectors corresponding to lambda equal to 0 are exactly equal to nullity. And if I know the nullity, then I know the rank. So suppose lambda is repeating just one time. Okay, suppose lambda is repeating one time. Then how many number of linearly independent eigenvectors? Linearly independent eigenvectors, which is exactly same as solution of x equal to 0. This is same as solution of x equal to 0. And this is same as nullity. So basically I can say the number of linearly independent eigenvectors are same as nullity. So if it is 1, see, corresponding to lambda equal to 0, here if it is repeating only one time, then it cannot be more than 1. It has to be exactly equal to 1. That's why from here I can say nullity is exactly equal to 1. That's why I can even infer the rank, which is exactly equal to 3 minus 1, which is 2. So that's why you can say that among all of these options, only C option is 2. Because nullity is 1, that is fixed, because lambda is just repeating, lambda equal to 0 is just repeating one time. But now let's just extend this question a little bit. Suppose instead of giving me this characteristic equation, they give me this characteristic equation. Okay, I mean, instead of the earlier characteristic equation was something like this, but instead of this they give me this kind of equation. Then lambda equal to 0 is repeating how many times? 2 times. Now interestingly, if any lambda repeats more than one time, then number of linearly independent eigenvectors could be just 1. At max, actually, if it is 2, then could be 2 also. It cannot be more than 2, right? So it could be 1 or could be 2. So rank, if there is no okay, maybe I can tell you like this. If there is no lambda equal to 0, I mean lambda non-zero, then rank is definitely n. Okay. If lambda equal to 0 is repeating 1 times, maybe something like this, then rank is definitely, it will decrease this rank by 1. Rank is definitely n minus 1. But if it is repeating, let's suppose if it is repeating, okay, suppose it is repeating, okay, let me not generalize it. I mean, okay, this is enough. So suppose it is repeating 2 times, then rank will be definitely less than n, but it could be n minus 1 depending on number of eigenvectors here. If that is 1, yes, it is n minus 1. If that is 2, then rank is n minus 2. It cannot be actually 3 because it is repeating just 2 times. So if it is repeating 2 times, then rank can be 3 minus 1, which means the number of linearly independent eigenvectors could be 1 or 2, which means nullity could be 1 or 2. So rank could be 3 minus 1. If it is repeating 2 times, then it can take away the rank by at most 2, okay, which is 2 and 1. So if it is repeating, let's suppose in general, if it is repeating lambda equal to 0, 0, 0, 3 times or 4 times, let's suppose, then this is 1, 2, 3. Then rank will be 7 minus, it could be minus 4. At max 4, it can take away the rank at max 4, 7 minus 4, or 3, or 2, or 1. Minimum 1, maximum 7 minus 4. I mean, maximum, you can say the rank could be 6, and the minimum rank should be 3 here. If my characteristic equation is something like this, where lambda is repeating 4 times, lambda minus 1 into lambda equal to 0 is repeating 4 times. I hope you understood like this. For this kind of equation, I can say the rank of the matrix A will be between this and this. That's the only information you can extract from this characteristic polynomial. But on top of this, if they also say that see the number of independent eigenvectors corresponding to lambda equal to 0 is just 1 or just 2, something like that. Based on that, I can exactly calculate the rank because I know the nullity in that case. I hope you understood this solution, right? That's very, very nice question. That's what we have taken from Berkeley University. I hope you understood the solution. So, like at Go classes, we are offering free engineering mathematics completely to boost your preparation, and we are also offering discrete mathematics. So these are the 2 courses that are being offered freely at Go classes. If you want, you can just check them out. I'm 100% sure that you will definitely like all of the videos of both of these free courses. Thank you so much.